Welcome students. So now we want to discuss homogeneous equations and Wronskian. So first recall from the last class, the superimposition principle. So what is the superimposition principle? If you start with a homogeneous differential equation of second order, y double prime plus 5y prime plus 6y equals to 0, then we saw that if y1, we saw that y1 is equals to e to the power minus 2t and y2 equals to e to the minus 3t is a solution for this differential equation. And not only that, we also saw that any linear combination of them is also a solution to this differential equation. So this uh, principle is called superimposition principle. So you are in some sense superimposing solution y1 and y2. Superimposing means taking linear combination of them. So this is true in general for homogeneous differential equation and is known as superimposition. Now, if y1 and y2 are solution to the y double prime plus p of ty prime plus q of ty equals to 0, then so is the linear combination of these, which is c1 y1 plus c2 y2 for any constant c1 and c2. So that can be checked by substituting. So we have already checked this, but you can check here by, since y1 and y2 are solutions, you can see that y1 double prime plus p of ty1 prime plus q of ty1 equals to 0. Similarly, you get y2 prime because y2 is also the solution. So p of ty2 prime plus q of ty2 equals to 0. Now multiply the equation 1 by c and equation 2 by, multiply the first one by c1. So let me call this 1, let me call this 2. So 1 times c1 plus 2 times c2 equation, you will get, if you combine it properly, you will get c y1 plus c y2. So c1 y1 plus c2 y2 double prime, because of the linearity of the derivative, pt c1 y1 plus c2 y2 prime plus c1 qt times c1 y1 plus c2 y2 equals to 0. So you see that c1 y1 plus c2 y2 is also a solution. And since there's nothing special about these constants, it works for all the constants c1 and c2. Now note that this is only, the superimposition principle is only true for homogeneous differential equation. All right. So this is an example of a non-homogeneous differential equation. Why? Because there is a constant there instead of a 0. So let's see. If this is non-zero, then it is non-homogeneous. Right? So let's work it out. So you can check that y1 equals to 1 is a solution, and y2 equals to 1 plus cos t is also a solution. Yeah, let's verify this. Verify. So we get what? Y1 prime double prime is 0. So we get y1 double prime plus y1 is basically 0 plus 1, which is 1, which is your RHS. Right? So y1 equals to 1 is a solution. Now what about y2? So let's see, y2 prime is minus sine t, y2 double prime is cos t with a minus sign. So therefore y2 double prime plus y is going to be minus cos t plus 1 plus cos t, which is going to be 1, which is same as right hand side. So these are, so y1, y2 are indeed, so they are indeed the solution. Yeah. So y1, y2 are solution. Now consider C1y1 plus C2y2. Now we get what is, so let's call this as y and check if this is a solution. So let's see. So we get C1, so we get y double prime plus y is going to be C1 y1 double prime plus C2 y2 double prime. Now that is what, so what is plus y, which is C1 y1 plus C2 y2, right? Now what is y1 double prime? That is 0. What do we get? C2 y2 double prime is what is, so we get C2 cos t plus C1 y1, so C1 times y1, which is 1, and C2 times 1 plus cos t, and check if this is really 1. If it is 1, then it satisfies the differential equation. But check, you can see if you take C1 and C2 equals to 1, if C1 and C2 equals to 1, then this becomes y1 plus y double prime plus y is going to be minus cos t plus 1 plus 1 plus cos t, which is 2, and of course 2 is not 1, so this is not equal to RHS. So this implies what? This implies what? That C1 y1 plus C2 y2 is not a solution. So this means the superimposition principle does not work for non-homogeneous differential equation. Now let's ask the following question, which we asked last time. So if you're given two solutions, y1 and y2, of a homogeneous differential equation, homogeneous means that this side is 0. Is it possible to get all the solutions by forming C1 y1 plus C2 y2 for some constant C1 and C2? So what does it mean? It means the following. The question we have is the following. If I take any solution of this differential equation, does it comes as a linear combination of y1 and y2? Yeah, and the answer is yes. So let's see. So consider the IVP. So let's work on this. So consider the initial value problem, y double prime plus p of t y prime plus q of t y equals to 0. All right, we are discussing only about homogeneous differential equation. Right? And since we are given IVP, we should be given some value initially. So y of t naught is, say, y naught, and y prime at t naught is going to be some other number. Let's call it y naught prime. Now, what do you want to show? Let y be any other solution, right? So let y be any solution to above IVP. Then what do we want? We want, so then is there C1 and C2 belonging to R such that y equals to C1 y1 plus C2 y2? Yeah. So now to show this, that any solution can be written as linear combination of these y1 and y2, we want to show, that is to show that such C1 and C2 exist. Yeah. So let's work on that. So let's see if such a C1 or C2 exist. So we have y equals to C1 y1 plus C2 y2, and we are trying to show that, oh, such a C exists, that such a C1 and C2 exist. So if you apply the what will be the derivative then? So we get C1 Y1 is this. So we get Y prime equals to C1 Y1 prime plus C2 Y2 prime. Now apply the initial conditions. So apply initial conditions. So let's apply the initial condition. So applying the initial condition will give us, what does it gives us? It gives us, for the first part, you will get, if you apply the first condition, you will get C1 Y1 of T naught plus C2 Y2 of T naught has to be Y naught. Okay. Then what else do we have? We have C2 Y2 of C1. Now we have to apply to this one. So we have C1 Y1 prime of T naught plus C2 Y2 prime of T naught equals to Y. So now let's look at this from the matrix format. So we have, if you write this in matrix format, you get Y1 evaluated at T naught. So this is some number times, Y2 T naught, Y1 prime T naught, Y2 prime T naught. So these are numbers, right? Because after all, they are functions, but evaluated at point T naught. So they are numbers. C1, C2 equals to Y0, Y0 prime. So now, if so let W be determinant of this side here, this matrix. So Y1 T naught, Y1 prime T naught, Y2 T naught, Y2 prime T naught. Now, which is going to be Y1 T naught times Y2 prime T naught minus Y1 prime T naught times Y2 of T naught, right? So determinant is cross. So determinant of 2 by 2 matrix, recall, determinant of A, B, C, D is AD minus BC, okay? So now recall, when we were discussing in your linear algebra, you would have discussed the following. So case 1, if W, this determinant is non-zero, there exists a unique solution to our system of equations. Unique solutions to what? Solutions to C1 and C2, right? Because that's what our goal is, to show that such C1 and C2 exist. And they are given by the following. So this is called Cramer's rule. You should look it up, Cramer's rule. They are given by C1 equals to 1 by W times determinant of. Now, when you're finding the first solution, what you have to do is you have to replace the first row. So in Cramer's rule, you have to replace this column by Y0 prime. Okay, so this is going to be, let me write this with a different pen to indicate what has changed. Y0 prime, and then Y2 T0 and Y2 prime of T0. And similarly, C2 is going to be 1 by W determinant of. Again, in this case, finding C2, you are replacing the second column. So you have First column will be as it is. And here you will have y0 prime. So you have shown that there exists a unique solution for C1 and C2. Yeah, this is what the Cramer's rule is. Now, case 2, when W equals to 0. If W equals to 0, then the system has has either no solution or infinitely many solutions. So you see this W plays a very important role in finding whether every solution y can be written as a linear combination of these y1 and y2, right? So this W matrix suddenly becomes very important. We should give it a name, and the name for this is Wronskian. So we call the determinant W as Wronskian of solution y1 and y2. Right. So sometimes it's also written as W equals to W of y1, y2 evaluated at t0. Yeah. So just to make clear that to make dependence on y1 and y2 explicit. So now we have the following theorem about the solutions then. So first theorem, if y1 and y2 are two solutions of homogeneous differential equation, y double prime plus pty prime plus qty equals to 0, and you are given this IVP along with y of t naught equals to y naught and y prime at t naught equals to y naught prime, then y equals to c1 y1 plus c2 y2, with c1 and c2 determined by initial condition and Wronskian, if and only if the Wronskian is non-zero. So it basically talks about the existence of solutions, and all the solutions be written as C1 Y1 plus C2 Y2, and C1 Y1 and C1 and C2 are determined by the initial condition, as you can see here, right? Okay, in here. Yeah. Now, second theorem is, suppose you have Y1 and Y2 are two solutions to this homogeneous differential equation, then the family of solution C1y1 plus C2y2 for all constant C1, C2 consist of all the possible solutions if and only if what W of y0, y1, y2 at t0 is non-zero for some t0. Yeah. So then in that case, we call y1. The proof of second solution, the second one follows from the first one. In this case, we call y1 and y2 are called a fundamental set of solutions. Now consider the importance of this. So if you take a second order homogeneous differential equation, all you need to do is find the fundamental set of the solutions, and every other solution is a linear combination of y1 and y2. Yeah. So your job is done if you can find the fundamental set, right? And in that case, we call, so then, and y equals to c1 y1t and c2 y2t is called general solution to our differential equation. Okay, so we have already worked this problem out. So we got y double prime plus 5y prime plus 6y equals to 0. We already saw last class that y1 equals to this and y2 equals to this are the solutions. So now let's see if they form a fundamental set. So what does it mean by fundamental set? So fundamental set is we need to compute the Wronskian. So what is Wronskian? Wronskian is determinant of y1t, y2t, or y1 prime t, y2t, y2 prime t. And let's compute this Wronskian. So we get what? We get determinant of e to the power minus 2t. Derivative of that is minus e to the power minus 2t. We get y2 is 3 e to the power minus 3t minus 3 e to the power minus 3t. And this determinant is going to be cross multiply. So we get e to the power minus 2t multiplied by minus 3 into minus 3t. Minus of minus makes it plus 2 e to the power minus 2t e to the power minus 3t. Now these powers add up. You can see that this is going to be minus 3 e to the power minus 5t plus 2 e to the power minus 5t, which is going to be minus e to the power minus 5t, which is non-zero for some t naught. In fact, for all t naught, right? I mean, like exponential functions for this form are never zero. In fact, for all t naught. Hence what? Hence y1 and y2 form a fundamental set. Set of solutions. Now consider the following problem now. So first, show that the function y1 equals to e to the power t, y2 equals to t e to the power t form a fundamental set of solution to this differential equation. Now, first of all, we have to check if they are solution, right? I mean, like, because for the previous one, we have already checked in past, but for this one, we haven't checked it. So let's check it out. So is this a solution, first of all? So we have substitute in this equation. So first show that y1 and y2 are the solutions. Before showing that they are fundamental solution, we have to show that they are the solution to DDE, just to make sure that we are talking about this differential equation. So let's compute. So we need y1 prime is going to be e to the power t, y1 double prime is also going to be e to the power t, right? Similarly, y2 prime is going to be t e to the power t plus e to the power t, which is same as t plus 1 e to the power t, and y2 double prime is same as t plus 2 e to the power t. You can check that. Yeah. So what do we get? For the first one, let's check for the first one, is it a solution? So we get y1 double prime minus 2y prime plus y1. So we get y1 double prime plus 2y prime plus y, and see if we get 0 or not. So in this case, we get y1 double prime is e to the power t minus 2 times y1 prime is also e to the power t. We are looking for the first one, power t, and then y1 itself is e to the power t equals to 0. So therefore, y1 is a solution. We have checked. Similarly, let's check for y2 now. y2 double prime plus 2 y2 prime plus y2. We get what? We get t plus 2 e to the power t minus 2y prime, so 2y2 prime, so that's going to be 2 times 1 plus t e to the power t plus y2, which is t e to the power t. Now to simplify this, I'm going to take all the e to the power t common, so I will get t plus 2 minus 2 minus 2t plus t. And you can see that t plus t minus 2t 0, 2 minus 2 0. So this is going to be 0 e to the t, which is 0. So y2 is also a solution. Solution to what? Solution to the DE. So we got, these are the solutions. Now we have to check, are these what? Are these the fundamental set of solutions? So how do we do that? We'll compute the Wronskian. So how do we compute Wronskian? So let's compute Wronskian. So we have W of y1, y2 evaluated at t is going to be y1 prime. So y1 is going to be simply e to the power t. y1 prime is also e to the power t. y2 is t e to the power t, and what? y2 prime is going to be t plus 1 e to the power t. And you're computing determinant of this, right? So I should say determinant of this guy. Now I can take, if you multiply, cross multiply, you'll see that e to the power t times e to the power t plus t plus 1 minus e to the power t times t e to the power t. Now take e to the power t plus e to the power t. So e to the power t times e to the power t is e to the power 2t. If you take that common, from the first one you'll get t plus 1. From second one you'll get t, which is e to the power 2t, which is non-zero for any t naught, right? The idea is that you have to show that Wronskian is non-zero at some point, right? So this is non-zero, therefore what? These solutions form a fundamental set, or these functions form a fundamental set of solution. Later on, when we see Abel's theorem, you'll see that once it's non-zero, it's going to be at a point, then it's going to be non-zero at every point. We'll see that later. So let's do the summary of what we have learned today. So two solutions, y1 and y2, of a linear second order homogeneous differential equation are fundamental if and only if the Wronskian, which is that determinant, evaluated at t naught is non-zero for some t naught. And in that case, the general solution is given by C1 y1 plus C2 y2. So thank you for your attention.